So we'll try that again. So we want to find the amount of energy associated with a group of charged particles placed at the corner of a square. So we'll say the square has side length s. And we'll start by indicating that when you place the first particle there, there's no electric field in that region of space. So the first particle costs you nothing, in that you don't have to work against any electric field to get the first particle there. Now, this might not be obvious to you guys, but the electric potential is not path dependent. It is path independent. So when we describe how much work it might take, all we really need to figure out is what is the total electric potential associated with assembling the group of charges. So with the first particle, since there was no electric field, the electric potential established in space, the electric field established in space will be based on the first charge placed there. So the first charge, Q, cost us nothing to get there. However, the second charge does cost us energy to get there. Before that charge is in place, the electric potential at this location is equal to Q over 4 pi epsilon naught times S. Now, the electric potential doesn't have direction. It is a scalar quantity. So it doesn't matter first what the path length was to calculate the electric potential at that point. And second, they just add together or subtract if the charges are negative. So when I say that the electric potential in this region of space conforms to this function, then at this point, the electric potential is merely that due to the electric field of the first charge. So if I place another charged particle there, another Q, the amount of potential energy will just be Q times the electric potential, which for this particle will be Q squared over 4 pi epsilon naught S. Now you're going to go around the square and do this for every charge that you add. Currently, the amount of potential energy associated with the system is this. Now, just an aside, if those were the only two particles in space, and I ask how much energy is associated with the system, this is the total energy associated with the system. A really common question is to say, I release this particle while holding this particle in place. How much kinetic energy would the particle have when it has traveled a large distance away? Which seems like a weird question to ask, but it's just a conservation of energy question. In fact, part of the reason we do study potentials is because they do have lots of stuff about energy. So if we release these two particles, this particle will just shoot away in that direction, gaining kinetic energy. Eventually, the potential energy the particle has will be converted to kinetic energy. Further still, you're supposed to be aware that we could calculate then perhaps how fast the particle's going. Same idea, same reason. So going back to our assembly of charges, putting the next charge in place really doesn't require us to do very much. We need to figure out what the electric potential is here due to the other two charges, and then multiply by the value of the new charge. The electric potential due to the other two charges isn't too tough because we've got one charge here, so that means the electric potential from that charge will be 4 pi epsilon naught S. And we have this charge here. You just have to be careful because this charge is a little further away. So its contribution to the electric potential is going to be Q over 4 pi epsilon naught. What should I put in there? Root of 2s, yeah. I'm sorry, not root of 2s. S divided by the root of 2. There. Which one is it? What is this distance, guys? This suggested you memorize it. Is it root of 2s, s divided by the root of 2, square root of 3 over 2 times s? Which one is it? Thank you. Want to make sure on a Monday morning we all are thinking the same things. So root of 2 times s. Now, it's not great. We can't add those two together, not easily. We're going to have something weird in the bottom. And you don't have to. That's the electric potential. Multiply it by Q, and you now have the total amount of energy associated with placing the third charge in place. Fourth charge, you kind of see a pattern developing, right? You guys kind of seeing what you have to do here? How many charges contribute to the electric potential at the fourth corner? So you're going to have to add up all of them, but two of them are exactly the same, right? The electric potential from this charge, electric potential from that charge are going to have the same contribution to the electric potential at that point. It's just this one that's going to be a little bit weird, and that's going to be a little further away. So we'll get 2q over 4 pi epsilon naught s plus root of 2s. And then the whole thing times Q for the amount of energy stored in the system. Assembling a group of charges. The total energy in this system has to be the sum of this energy plus this energy plus this energy. Can you kind of see that they're going to get things that add together? If I look closely, I've got one of these, two of these, four of these. Right? 2 plus 1 plus 1. Are we okay with that? So when we start looking at the total amount of potential energy, there'll be 4 q squared over 4 pi epsilon naught s. And then I have one of these and another one of these. So plus 2 q squared over 4 pi epsilon naught root of 2s. And this represents the total energy for your assembly of charges.
Where did you get q squared from?
I distributed the q here inside.
Oh, okay. And then also, why don't you add the original q?
This is the original energy here.
Oh, okay.
Right, this is the first charge doesn't cost us any energy to get there.
Oh.
Right, so there's nothing to add for that one. Does that make sense?
Yeah.
Okay. So assembly of charges just looks like this. There's nothing special about it. The whole point about assembling charges is that it takes energy to get a group of charges together because they're trying to push each other apart. Now, there's lots of kind of exercises about this. For example, one of the more common will look something like this. Two positive charges are equidistant from a number line or a point in space. We'll say they're a distance d away from the line, and they have charge q. You have a third charge, q, that is a long distance away. What velocity must you send in this charge so it can make it to the point between the two charges? So you're going to fire this particle from the right so that it makes it just to this point. How much velocity do you give that particle? Assume the particle has mass m, charge q, and is infinitely far away from your two charges that are stuck in space. This is ultimately a conservation of energy question. You need to figure out how much kinetic energy must be given to this particle so that it will convert all of that energy to potential energy right as it makes it to this point between the two charges. And you don't have to know how far away the particle is. All you need to know is what is the electric potential right there. Once you know the electric potential right there, you know exactly how much energy it takes to get there. Try it. Give me an expression for the velocity. This one should be pretty straightforward if you follow along with what we just did. There's not very much work here, and a quick walk around the back table suggested that you guys see that too. The electric potential at that spot ended up being just Q squared over 4 pi epsilon naught d times 2 for 2 particles. That means the total, the electric potential is just Q. The electric potential energy will be 2Q squared over 4 pi epsilon naught times d. All you had to do is set that equal to 1/2 mv squared, and now you can solve that for v. Now, because our other one was little q, we probably should write that as capital Q and little q to be accurate and to be in the terms that were given. Anthony?
I was just going to say.
All right. Now, a few other little things I want to talk to you about. They're kind of side conversations, but I want you to imagine I'm looking at a spot at the center of a square. I have 4 charges. They are equal and opposite. The blue charges are negative and the yellow charges are positive. Right now, I've set up a configuration in which the electric field is 0 at the center of the square. What's the electric potential at the center of the square? Bless you. This shouldn't be tough. Can you explain why it's 0? What's that? I'm not sure I'd use the word counteract, but this distance is the same for all, right? So same distance away. If we're dealing with the electric potential from a point charge, we know it's based on distance, and they're all the same distance, they're all the same charges, but I have this one's positive, this one's negative, so the sum of their potentials will add to be 0. Similarly, positive and negative, the sum of their potentials will add to be 0. So although in this configuration, the electric field is 0 and the electric potential is 0, is there any way to shift these particles around so that you can create an electric potential at the center? Go ahead. So I switch one of the yellow and blue ones. Now there's clearly an electric field at the center. Can you guys point in the direction of the electric field at the center? Let's see, only 3 of you are pointing. That's not very many. I said the blue ones are negative and the yellow ones are positive. All right, good. So to the right is the direction of our electric field. Electric potential is still 0 though. Right, even though the electric field points in one direction because we have not balanced charges in such a way that balance the electric field, the electric potential is not a vector. So the sum of the electric potentials is still 0. Is there any way to arrange these charges to have an electric potential that is other than 0? Now, if I were to change the charges so that, say, they're all positive, is there an electric field at the center? No electric field at the center. Is there electric potential at the center? Yes, it would take energy to get to the center of this square. Now, this part is a little bit, I think, challenging to wrap your head around. If I take a particle from far away and place it at the center, how much potential energy would it have in this arrangement? It would have 0 potential energy. If the electric potential is 0 there, then the particle will have 0 energy there as well. And it doesn't always jive with some of the things we think. If we let this particle go, it will be accelerated to the right because it will experience an electric field. But it takes no energy to get the particle there because the electric potential is zero. It's like placing it at ground level, but there's a hole next to ground level so it can roll into it. Now, the weird thing is, if I place 4 charges like this and then say that I'm going to bring in this charge from a faraway distance, it takes energy to get to that point. But once there, the particle's trapped there. The electric field is zero. If I release it, it won't go anywhere. But it took energy to get to this point. So when dealing with the electric potential, one of the things to be careful about is because we have positive and negative charges, we can have configurations in which the electric potential is zero, but there exists an electric field, or there exists an electric field, there doesn't exist an electric field, but the electric potential is not zero. These are all reasonable things that you have to consider. Do you remember the electric field both in and out of a conductor of charge? I'm sorry, not a conductor. Let's go with an insulator first, an insulator of charge. It's one of those problems that we could use Coulomb's law to figure, or Gauss's law to figure out, but it should still be in your notes. In fact, if we say the whole thing had charge Q, I'll give you the outside one. So if it's a radius of capital R, we know that the electric field outside of this has got to be Q over 4 pi epsilon naught R squared when R is greater than R. Do you remember what it's like when it's inside? Okay, let's answer this question. It's in your notes. Find it, please. You're organized people. Go ahead. I know we have 10 minutes. So even in this configuration or this situation where we know the electric field dies to zero as you go towards the center, it would take a lot of energy to get to the edge, probably something that would look of this shape, just to get to the edge. But then as you push from the edge to the inside, you would still have to push against an electric field. So the electric potential will increase as you move your way towards the inside of this sphere, because there's a clear electric field inside the sphere still.